Yes, this is a very quickly introduction to autometry package, which is necessary when you're going to do navigation, and that is what you are going to do sooner or later. And what is here is an example program I found on the net, which I will explain very short. Um, Compared to the other square and circles you have done, then you can see there is an include of a so-called transform library, which is also introduced in the ROS Wiki tutorials about navigation. And then we have the geometric message twist, which has the command velocity topic in its topics. And then there is actually also an library called Pose 2D. Pose is actually about the x, y, and angle coordinates in one plane, therefore 2D. And then the navigation message, because the odometry is publishing data. So when the robot is moving, then it is publishing to an odom topic, which our application here for navigation, we must subscribe to that. Then there is also a math library, but I'm not sure if it is necessary. Now, if you then jump down to the main, then we have the angles are always in radians, therefore they have defined a pi constant, and very useful printout on the console is ROS info. So if you use that and then in quotation, just as if you know printf, you can use it exactly in the same way. So what you see down here is an ROS info where I have printed out the XY angle coordinates to follow actually how the robot is moving and how less precise it is. And here you have the first, you see here, it is start. This is here, start. Now, so then we have the need here, as I said, for subscribing. We have to subscribe to the odom topic to get the information about the position x, y, and the angle theta. And when we subscribe, we need to have an callback function. So this is an so-called pointer to an callback functions, which we must describe and implement. Then we have the well-known twist, the command topic, command velocity, where we move the robot as you used in your assignment 1. And then we have the advertising publisher, yeah, and you can see that is relying on this pose 2 dimension. So it is to get the advertisement from the position. Now, and then the frequency or the rate which is it runs with. And if we then go to the callback function first here, then we have the callback function up here at the top. It can be in principle, yeah, it must be in the top as you use this one. Here is the reference to it, and therefore you must have it specified before you go into main. Therefore it is up here. And then you can see here that we have have the pose here is a part of the odometry, and it has the position X, Y, and that is put into our odometry parameter in application here called current pose.x and Y. And then I use my ROS info here, as you can see here, and it is exactly as printf. And if we then look down here, then we can follow the X, Y position and the theta, and the theta is coming out of this so-called criterion, which is based on the odometry data, and then we have the trigonometric functions, and we get a nice conversion to an angle actually. So we get the angle here, the so-called yaw is got from here. But we need to have this declaration here. So it's the message here is used for that, and the yeah, that's more or less what it is about. You can see here the current pose here is of that type here, pose 2. So it is, we get it converted to the current position, if we can say so. So that is the callback function, and we use these parameters down in the main to move the robot. But we can say a feedback, so we know here the physical position, so we can drive to that position instead of using the time as we did in the first assignment. Now we need to have an subscriber reference, or it's an object. We can say it's an object actually of the subscriber class, and we have the need for a publisher. The subscriber is to retrieve the odometry, and the publisher is to move the robot. Now, and then we have this advertisement belonging to this pose. So then we have the need for an object of the twist, so we can configure the parameters in the object. We configure them, we initialize the X, Y, Z, and we publish. That means we have it stopped. Then we say move forward, and we have the need for have a time here, and then we have the while as we had in the assignment, but here you can see we use the current pose.x, and then we say run 0.4 meter up to that, and then we move linearly, publish, spin once, and we keep going there until we reach that distance. Then we turn right, and here we use, you can see the theta, the angle calculated in the callback function, and it turns clockwise, and that is then becoming negative. The angle is starting on 0, and if we count clockwise, then it becomes negative. So minus 90 degrees, it has to move, and it has to move that speed. Then we can move forward, and now we are in an XY coordinate system, and if we go below the X down of in the coordinate xy, yeah, then the y coordinate becomes negative. So we move to the corner minus no 0.4 comma minus 0.4, and then we have to turn again, and this is a little bit tricky because the angle is suddenly turning over from minus pi to plus pi, and that means we have to turn until we reach that point where it turns over. So it's another 90-degree clockwise, and then we can move forward until we get back. We are now running back on the x coordinate, and I have not the y coordinate. So that was an explanation, but it is an feedback loop we have created here, because we are using the position combined with the velocity instead of using the time. And for navigation, you absolutely need to have the position taking that into account as well. That's all.